Now let us proceed with our discussions with the other terminology about shrinkage. We have gauge factor, which is the ratio of the rate of resistance variations caused by uniaxial stress applied along the shrinkage. Simply said, the fundamental principles of the shrinkage is about the electrical resistance. The shrinkage itself has its own resistance at the original state. Whichever deformations induced onto the shrinkage will lead to changes of the resistance. As long as we can quantify the changes of the resistance, we are able to estimate the strength experienced by the shrinkage due to the uniaxial stress. We know that the electric resistance changes proportionally to the mechanical deformation. When the shrinkage extended, the sensitive elements on the shrinkage elongates. This reduces the cross-sectional area and increases the resistance of the shrinkage. Now, if the shrinkage shortens, the sensitive elements on the shrinkage shrinks. This leads to a larger cross-sectional area and lower resistance of the shrinkage. The deformations is now proportional to the electric resistance. By quantifying the change of the resistance against the original resistance, we can estimate the strength happening within the material. Of course, it will require a conversion of this ratio into the strength. Now, this ratio here is known as the gauge factor. As far as the data logger is concerned, the data logger is actually measuring the change of resistance. The computations will be finding the ratio between the change of resistance against the original resistance. Now, if we key in the gauge factor into the data logger will help to compute the strength, and as a result, the strength is displayed. For you to acquire the gauge factor, you will need to refer to the specifications given by the shrinkage. You can find these specifications on the package of the shrinkage. For this type of shrinkage, the gauge factors is given as 2.12 plus minus 1%. By dividing this with the K, you are able to determine the strength happening in the shrinkage. Next, we talk about the axial sensitivity. The axial sensitivity is very similar to the gauge factor. It refers to the sensitivity of the gauge when no strength is applied in the directions perpendicular to the gauge axis. And then we have the transverse sensitivity. You know that a material undergoing deformations in one direction will also lead to the deformations in another direction. This is due to the effect of Poisson ratio. That's why you will see a member to be elongated and shrink diagonally. There will be deformations in two directions. For a typical steel, the Poisson ratio is about 0.2 something. That means the deformations in the lateral directions is about 20 something percentage as compared to the longitudinal direction. It is very minor, but the deformation exists. Sometimes you will need to also know the transverse sensitivity, especially in the case of high precision measurements or in the locations where biaxial strengths occur. This might influence the results. There will be a factor for the transverse sensitivity. You will need to refer to the specifications of the shrinkage. or you may refer to the transverse sensitivity ratio. This is the ratio of the transverse sensitivity to the axial sensitivity. It is usually equals or less than 1%. This is applicable for normal case, except in high precision measurements or in locations with biaxial strength. You may refer to the specifications given by the shrinkage. For this type of shrinkage, it is stated that the transverse sensitivity equals to 0.1%. Next, we talk about the shrinkage frequency response. It is referring to the longitudinal elastic wave speed of the test specimen. This wave speed differs by the gauge length, as listed by the table here. You will see that the shrinkage used to measure the strength of the steel are in the range of 0.2 mm to 10 mm. The wave speed is given here. As for the concrete, the gauge length differs from 10 mm to 60 mm. The gauge length for shrinkage used to measure concrete is normally bigger than the steel due to the size of the aggregate. Theoretically, the size of the shrinkage should be greater than the maximum size of the aggregate in the concrete. This is to prevent the strength or crack bypass the shrinkage during the measurement, which result in inaccurate measurement. In common practice, let's say now the maximum aggregate size of the concrete is 20 mm. We will use the shrinkage with the size of 3 times the maximum size of the aggregate, which is 60 mm. Now the frequency response differs. The one that we commonly use for steel bar, it would be 5 mm. The frequency response of the shrinkage is 270 kHz. The frequency response limits are typically only a concern under impact conditions. What does it mean by the impact condition? It means that the specimen is subjected to a sudden or instantaneous load where the magnitude increases significantly within very short period of time. Now you will need high frequency response in order to extract sufficient data throughout the short period of impact. Of course, if the frequency is higher, you are able to get more data within a second. If the frequency response is lower, the amount of data that you can acquire within a second reduces. However, for typical usage, such as static load, the frequency response is not a concern. You don't have to worry about that. Next is about the gauge resistance. Previously, we mentioned about the principles of the shrinkage, which is actually measuring the electric resistance. And the shrinkage has its own resistance originally. Now, this gauge resistance is referring to the original resistance of the shrinkage, and it is referring to electrical resistance of an unbounded gauge at the room temperature subjected to no external pressure. That means under normal conditions, without any deformations, the shrinkage has its own gauge resistance, and this is normally specified in the specifications of the shrinkage. The most common one, it will be 120 ohm resistance. There are also 60 ohm, 350 ohm, and also 1000 ohm. If for normal applications, you can just choose 120 ohm. Now, high resistance gauge use a high bridge output, and then high voltage are applied but they are more susceptible to noise. What does it mean? Remember, we talk about shrinkage is actually measuring the change of the electrical resistance. If you have higher degree of the resistance, it becomes more sensitive. The variations, it will be 1 out of 1000 parts. You are talking about a ratio between the variations of resistance against its original resistance. Now, if you are using 60 ohm, the variations, it will be 1 out of 60 parts. It will become less sensitive. You know that when it comes to the measurement, it doesn't mean that the more sensitive it is, the better. When the measurement is too sensitive, there may be noise, and this will affect the results. The sensitivity should be just enough, not too low and not too high. Personally, I feel 120 ohm is already sensitive enough. You will see fluctuations in terms of the reading, even though you did not induce any force onto the material. Unless you need it to be highly precise, 120 ohm is good enough.